All right, rapid recap of where we were back before break. We were doing pH calculations, and we started with strong acids or strong bases. There we said the calculation is pretty straightforward because if you have a strong acid, whatever your concentration of strong acid is, that's a concentration of H+. You take the negative log and you get the pH. For a strong base, you take the concentration of the strong base, you figure out the concentration of OH-, and you take the negative log, that gives you POH, and then you subtract that from 14, you get pH. So strong acids and bases, pH calculations, pretty straightforward. Weak acids and weak bases, slightly more complicated because there we need Rice charts. Now we have something that's going to come to equilibrium, not completely dissociate, so we need a Rice chart to figure out how much of it actually dissociates. So you do a Rice chart calculation, you set up your equilibrium expression, you set that equal to the Ka value in the case of a weak acid, or the Kb value in the case of a weak base. And you solve, you get the concentration of H+ or OH- at equilibrium, take the negative log, and you find the pH that way. The last example we did was an acidic salt. So for an acidic salt, there the key was we have a spectator ion. In NH4Cl, if you think about it as two different ions, NH4+ and Cl-, NH4+ is a weak acid, whereas Cl- is not basic at all. So Cl- just acts as a spectator. So we just focused on the NH4+. So there was one extra mental step there when we had a salt and we're trying to determine the pH of the solution. So now let's try a basic salt. Conceptually, it's going to be very similar. So first thing you're going to have to do is think about, okay, what are the ions it splits into? Then you think about, okay, is one of them acidic? Is one of them basic? One of them is going to be a spectator. And then identify the equilibrium that you need to examine. So if we want the pH of a 0.5 molar solution of NaF, where might you find NaF in your everyday life? Toothpaste, exactly. Yeah. Sodium fluoride. Your toothpaste probably has that as a key ingredient. Gum does not have fluoride. Drinking water has a small amount of sodium fluoride in it. It's fluoridated. Student question is, in Colorado, don't they have more fluoride in the water? I don't know. That's a good question. I mean, so there is a condition called fluoridosis. If you consume too much fluoride, it can start to color your teeth, and it might have negative health consequences that I'm not sure exactly what they are. But they're usually you don't get it from the drinking water. Usually you would get it from foods that you eat, particularly if you eat things like raisins. If they have been irrigated using fluoridated water, what happens then is now you grow the raisins, you have all this fluoridated water there, so there's lots of fluoride in the grapes, and then you dry them out to make raisins, and now you've concentrated the fluoride because you've got rid of all the water. And so there are, raisins are a food that's actually very high in fluoride. All right, so that's a little side note. Now go ahead, think about what the concentration, what the pH of a 0.5 molar solution of sodium fluoride is going to be. Collaborate with each other. Just to be clear, when we talk about solutions, we're always talking about aqueous solutions unless indicated otherwise. So when I say a 0.5 molar solution of NaF, that means in water. All right, I think everyone's sufficiently confused. So let's start from the beginning. NaF, when I put that in water, what two things does it split into? Na plus ions and fluoride ions. All right. So one of those is going to be a spectator ion. Which one of those has no acid-base properties at all? Sodium plus. All right, sodium plus. This is totally a spectator. I mean, it's always a spectator, right? Even in our precipitation reactions, sodium ions are just destined to just dissolve, and that's it. They just watch everything happen. Whereas fluoride, we know fluoride is the conjugate base of a weak acid. So that means it's going to be at least somewhat basic. So the mistake that I'm seeing a lot is people writing now saying, oh, F minus, so I'm going to write my reaction, and I don't want you to write this down. But a number of people have said, all right, maybe my reaction is going to be HF goes to H plus F minus. The problem with that is we don't actually have HF to start with. We just have F minus. Some people, instead of that, wrote that equation in reverse. So some people wrote this, H plus F minus makes HF. Well, that would be okay if we had a solution with H plus and F minus in it. But we don't. What do we actually have that will react with F minus? Water. What we have is F minus can react with water to make HF and OH minus. So when you have a weak base, you always want to write the equation of base plus water makes conjugate acid plus OH minus. And so then the next mental step we need to do, now that we've written that equation, we need to know what its K value is. So I need to know what is the Kb value for F minus. And so you look at your blue sheet and you're like, all right, I'm going to go to the Kb list. And on the Kb list, you look and you see not fluoride, not fluoride, not fluoride, not fluoride, not fluoride, not fluoride. Oh, fluoride is not on your Kb list. Why isn't fluoride on the Kb list? Because, well, fluoride is not an acid. Fluoride is a weak base, but why isn't it on the Kb list? Well, look at everything on the Kb list. They're all neutral, right? So that's a list of neutral bases. If I want the Kb of a negative base, what I really should look up is the Ka of its conjugate acid. So remember, for a conjugate pair, Ka times Kb equals Kw. And so if I look up the Ka for the conjugate acid, I can find the Kb. Kb of F minus is going to equal Kw divided by Ka of HF. Who knows the value of Kw? Yeah, 1.0 times 10 to the negative 14th. I usually just leave the 1.0 part out. And that's going to be divided by the Ka of HF. That is on your blue sheet. And it's, what, 7.2 times 10 to the negative 4th? All right. 1.4 times 10 to the negative 11th. All right. So that's a really small KB value. Our KB values usually range from about, 10 to the negative 3 to 10 to the negative 12 or something. This is on the really low end. So that means we shouldn't expect the solution to get very basic, but it's still going to get somewhat basic. All right, so I have my reaction. I have my K value. I've got to finish the rice chart. We're going to do this in moles per liter. What's my initial concentration of F minus? 0.5 molar. Do I care about water? No. I mean, I do care about water in my real life, but in this problem, I don't care about the concentration of water. Initial concentration of HF, 0, OH minus, 0. All right, you can fill out the rest while I fill out the rest. How can I make solving simpler? KB is really, really small, so 0.5 minus x is roughly equal to 0.5. All right, so we get x squared over 0.5 is 1.4 times 10 to the negative 11th. So x squared is going to be 7 times 10 to the negative 12th. Square root of 7 is going to be 2 point something, 2.6. Square root of 10 to the negative 12th is 10 to the negative 6th. So I get 2.6 times 10 to the negative 6th. That x represents what? Concentration of OH minus. All right, now that I have the concentration of OH minus, how am I going to get to pH? First, find the POH, and then subtract from 14. Oh, I didn't leave myself enough room. Sorry, guys. So the POH is going to be 5.6. All right. And so the pH It's going to be 14 minus 5.6, so 8.4. So relatively high concentration of F minus, you know, it's not a very basic solution at all. It's only very slightly basic because F minus is quite a weak base. Question. So the question is, on the pH scale, what numbers would you consider like really acidic or really basic? I mean, it's a spectrum like anything else. So 7 is neutral. You know, 8.4 is slightly on the basic side. How basic that is depends on the application. So like if we're talking about the water in your swimming pool, this would be way too basic. Your eyes would be burning. You would be uncomfortable in that, you know. If we're talking about, you know, in a chemistry lab, you certainly can make much more basic solutions than that. So the question is that why chlorine's totally fine to be in the pool? Well, chlorine, remember when we talk about adding chlorine to the pool, we are talking about Cl2, or usually more like sodium hypochlorite. So what chlorine's role there is to kill bacteria, and it does have some effect on the pH because it's not chloride. But if you add chloride, it won't affect the pH at all. Yeah. All right. Let's do one more example. We mentioned in the last lecture, hopefully you've watched it by now, but if you haven't, some metal ions can be acidic. So AlNO33, when I have a salt like that, it's going to split up into Al3 plus. And NO3 minus. Well, what do we know about NO3 minus, first of all? It's always soluble. What's its conjugate acid? Nitric acid, which is strong. So this is the conjugate base of a strong acid. So that means it's not basic at all. So in this case, spectator ion, we're not concerned about that. Now you look at aluminum 3 plus and you say, well, that doesn't have any H plus. So clearly that can't affect the pH either. But that would be an overly simplistic view. So it turns out things like aluminum 3 plus, when they dissolve in water, they make these complexes with water. So it'll get surrounded by water. And now if you look at your Ka list, you might run across this thing. Question. Question is that because it's a metalloid? And the answer is no. Aluminum actually isn't a metalloid. Even though it's near that dividing line, aluminum lies squarely in the metal camp. All right, so the question is, what's special about aluminum? All right, I'll do a little digression back into last lecture. All right. So the idea is this: you have Lewis acids like aluminum 3 plus. Lewis acids are electron pair acceptors. And what happens when you dissolve aluminum 3 plus in water, aluminum 3 plus has this positive charge. And water's the lone pairs on oxygen are like, ooh, I like you. You know, they really are attracted to the positive charge in aluminum. And so each water molecule shares a lone pair with aluminum. And what that does is weakens the OH bonds just slightly so that these water molecules that are bonded to aluminum become slightly more acidic than they were before. Now, what's special about aluminum is aluminum has very high charge concentration. So it's actually very attractive to those water molecules. Why does aluminum have very high charge concentration? Because it's got a +3 charge, and it's relatively small, because it's only in the third row of the periodic table. +3 charge means lots of charge, relatively small because it's relatively high up the periodic table. It's not like, gold or silver or platinum or tungsten, those things further down the periodic table that are much bigger. So aluminum, an aluminum 3+ ion is a really small, concentrated positive charge. And so that makes it particularly attractive to the water molecules. And so this effect is really great for aluminum 3+. Some other relatively small, relatively high charge concentration ions like iron 3+ are also somewhat acidic for the same reason. But this is also why group 1 ions like sodium+ or potassium+ with just a +1 charge, they don't really have this property because the charge is not as concentrated. So they don't attract the water molecules as strongly. All right. So it turns out aluminum 3+ is, among all the metal ions, the one that acidifies water the best. And it does that by bonding with the lone pairs of the water and making one of those hydrogens a little more willing to break off as H+. So if you look at your Ka list, there's only one metal ion listed. And it's, what's the name that they give it on the Ka list? Hydrated aluminum 3+ ion, right? So this is, oops. This is hydrated aluminum 3 ion. And that is on your Ka list. Question? The student question is, would this prevent the aluminum, with the formation of this hydration shell around it, prevent it from forming a precipitate? The answer is no. It can still precipitate. So when it precipitates, that just means some other ion is attracting it more strongly than the water does. So you can definitely add certain ions to an aluminum 3+ solution that will precipitate it out, because the ions attract the silver, not silver, the aluminum ions more strongly than the water molecules do. And that's what solubility of ionic compounds really is all about. It's like, who is more attractive to the ions, the water molecules or the oppositely charged ions? So we have this is on the Ka list. So we're going to write a Rice chart for that thing dissociating. So this is just like any other acidic salt, except it just feels a little weirder because the H+ isn't already part of the ion itself. So the equilibrium that we're going to look at is AlH2O6 3+ dissociating into H+, and, well, if you think about what's left behind, we have aluminum. It's bonded to how many full water molecules now? 5. And OH. And the total charge now is 2+. Now I'll give you a little tip. When you are solving problems like this with a Rice chart with an acid equilibrium, essentially all acid equilibria are the same. It's just different other parts of the molecule. So if you wanted to save yourself when you're solving the problem from having to write out AlH2O6 3+ and AlH2O5 OH2+, that's kind of a pain. You're always welcome to just write it this way. You're always welcome to just do the Rice chart that way without writing out the specific acid involved. I do that all the time because it just makes life easier. All right, but other than that, this problem is going to be the same as all the others we've done so far. Fill in your initial concentration, fill in your changes, set up the equilibrium expression, and solve. So go ahead and do that. So like 2.3 or 2.4? All right, so in the end, the concentration of H plus is 2.4 times 10 to the negative 3. The pH is 2.6. All right. There we go. All right, what questions do you have? All right, you'll get lots of practice with this on the problem set. Now I want to do a couple of questions that get a little conceptual rather than just calculations. So let's say we needed to generate particulate drawings. So drawings that show the dissolved particles. This is a thing that has been introduced in the AP test in the last year, last year, and it'll be on this year. That forces you to think about what's going on in two solutions. So let's say we have the beaker on the left is HNO3, the beaker on the right is HF, and both solutions have the same pH. What would have to be the same about the two drawings? Same concentration of H+, yeah. So the representations would have to be similar because they have to show the same concentration of H+. Now to get the same concentration of H+, in a solution of HNO3 and a solution of HF, how would they have to be different? All right, there have to be different concentrations, really, of the two acids. In particular, which one would we need more of? Which one would we need to dissolve more of to make a pH of 4? HF or HNO3? All right, so the answer is HNO3. Why? All right, you have the explanation exactly right, but you flipped which one's the strong and which one's the weak acid. So HNO3 is strong. Since it's a strong acid, less of it is needed to make a pH of 4. HF is a weak acid, so more of it is going to be needed. So in each of these, I'm going to have the same concentration of H+. Let's say the concentration of H+, to make a pH of 4, in my representation, I'm going to put 2 H+ ions in each beaker. So they'd have the same concentration of H+, so they'd each have 2 H+ ions. So what else would be in the HNO3 beaker? I picked a random number for how many H pluses to draw. I knew that they'd have to have the same concentration of H+. I chose 2 just because it's a small number and it's more than 1. 1 just felt like not quite enough. Oh, sorry. Up here at the top, I had written less needed to make the pH equal 5, but I meant to make the pH equal 4. All right, so in the HNO3 beaker, what other things are going to be dissolved? There'll be 2 NO3 minus ions dissolved in the HNO3 beaker. Anything else? Would I have any HNO3 molecules dissolved there? No way. Why not? Because 100% of strong acid molecules dissociate. All right. So the beaker on the left would look like that. The beaker on the right now, conceptually, without doing any calculation, what do we know has to be different? There's definitely going to be some HF molecules that are undissociated. So I know over here I'm going to have some HF molecules that are undissociated. And does a relatively high percentage or a relatively low percentage of a weak acid molecules dissociate? Relatively low. So probably if there's 2 H pluses, there's going to have to be a bunch of HFs in here. Maybe more than I could even draw. I don't know. What else has to be in there? F minuses, how many? 2. So we'd have to dissolve a lot more HF to get to the same pH as we would HNO3. Now, if I wanted to actually calculate how much HF, any ideas how I would do that? I'd have to use a rice chart. Here, let me see. To actually figure out how many HF molecules or what percentage of the HF molecules were dissociated, I'd have to set up a rice chart where I had what? Where I have HF dissociating into H plus and F minus. Now, what's going to be interesting about this is, what's the thing that I don't know? I don't know the initial concentration of HF. So this is actually going to be X, and this is going to be 0 and 0. But I know the pH, so I know what? Concentration of H plus at equilibrium. If the pH is 4, then the concentration of H plus is going to equal 10 to the negative 4th. So this is going to be 10 to the negative 4th, which means this had to be plus 10 to the negative 4th. So concentration of F minus would do the same thing, 10 to the negative 4th. Oops. So here we'd get X minus 10 to the negative 4th. So this would be just a different kind of question, one where we know the pH, but we don't know how much HF we had to dissolve. But we would set up the rice chart the same way. It's just now the variable is the initial concentration. And now we'd set up the equilibrium expression, which is Ka equals concentration of H plus times F minus over concentration of HF. And so that's 10 to the negative 4th times 10 to the negative 4th over X minus 10 to the negative 4th. And then where would I get the Ka value to set it equal to? From the blue sheet, 7.2 times 10 to the negative 4th. So now I get 10 to the negative 8th equals X minus 10 to the negative 4th times 7.2 times 10 to the negative 4th. It's just an algebra problem now, and we could actually solve it. So this actually, I'm glad we did this. Because it makes a good point. I dissolved 1.14 times 10 to the negative fourth. Turns out at this low a concentration, what percentage of them actually dissociated? Not all. It's 10 to the negative fourth over 1.14 times 10 to the negative fourth. So it's like 90%. 86%. All right. Yeah, it's different from what I said at first. So here's why. In a really dilute solution, usually more of your acid dissociates. As you add more and more of it, a smaller and smaller percentage dissociates. So at this dilute concentration, actually it's mostly dissociated. If we made it more concentrated, it would get less dissociated. So going back, I can correct my picture then, because I had made very few of them dissociate. Now I would have to make most of them dissociate. Oh, I can't erase now. I'm just going to have to cross some of them out. So really there would be like maybe one HF molecule undissociated in my picture. And to do this better, I might even have to, in a perfect world, I would probably have to draw more H pluses, right? I'd have to draw 10 H pluses and have, or 8 H pluses for every one undissociated HF. 7 H pluses. All right. Sorry, I'm trying to do the percentage in my head. So the question is, this is a weak acid still. It's a weak acid because it's not 100% dissociated. And if we looked at the percent dissociation, if we made a more concentrated solution, like if we had made this a pH of 1 or 2, at a pH of 1 or 2, there'd be a lot fewer HFs dissociated. It'd be mostly undissociated. But because this is so dilute, most of them dissociate. All right. So here's another one, and now this one, this drawing's not actually on your notes. So what I want you to do is repeat these drawings in your notes. So this is going the other direction. What if I give you the two drawings? What conclusion can you draw from them? All right, what can we determine from these diagrams? All right, HY is more acidic, meaning HY is a what acid? Stronger acid. So HY is stronger than HX. The right one has a lower pH, higher concentration of H plus. So this would have a higher concentration of H plus, which would be a lower pH. So this would be 1 molar of HX dissolved and 1 molar of HY dissolved. Yeah, the previous one, we had two solutions, both were the same pH. This one, they're the same initial concentrations of the acids. And if we wanted to mathematically, we could actually go and calculate what the Ka values for each of these was based on what percentage of them actually dissociated. All right, so that's the idea. You want to think of acid strength as being related to percent dissociation. I think what we'll do, we just have one slide left, really. We're going to draw a clear distinction between pH and pKa, but I want to take my time with doing that to make sure that the distinction becomes clear. So we'll come back to that discussion very briefly on Wednesday, I guess.